All right, chemistry, this is your video lecture for chapter 3. A combined section with sections 1 and 2 will appear on the same quiz. We're going to be covering it all at once. So here we go. This section is titled The Atom, from Philosophical Idea to Scientific Theory. As far as what I want you to be able to do at the end of this video, too far, sorry. Explain the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. These are some fundamental laws of the natural universe. Summarize the 5 essential points of Dalton's atomic theory, and then explain the relationship between Dalton's atomic theory and the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So we have these fundamental laws, and we have this this set of 5 points that construct John Dalton's, the guy's name, his first real atomic theory, the idea of what an atom is, and we want to connect these fundamental laws with Dalton's atomic theory and see how they connect. So let's get started. So when I say atomic theory, we're talking about the idea of the atom. And yes, it is considered atomic theory because what the atom is truly not known in its full capacity. And so any description of what an atom is truly is a theory. It's not a law. It's not a fully, completely described thing. Even if you consider quantum mechanics, there's still quite a bit that's unknown about the quantum level and how things operate on that level. So we say atomic theory. Now the idea of an atomic theory is more than 2,000 years old. And until recently, scientists had never seen evidence of the atoms. And so a 2,000-year-old idea, we've only had empirical evidence to support the existence of atoms for about the last 200-ish, 150, 200 years. Now, the law of definite proportions, the law of conservation of mass, and the law of multiple proportions support the current atomic theory. That's why we're going to talk about them at once. These particular fundamental laws, there are more fundamental laws than just these 3, but we're going to look at these 3 because they do build into our current atomic model. And so we have this figure down here at the bottom right, 2 pictures of atoms, and they both represent an atom. But here's the thing. The one on the left is a picture of an atom, a drawing of an atom that you may have seen before. You might recognize this as an atom. You might not know why, but you might think this is an atom. Now, at a certain point in history, yes, this was believed to be the true form of an atom, but we now know that's not entirely accurate. We now know that something a little bit closer to what's on the right is the actual, a better representation of the true form of an atom. Let's get started with those fundamental laws. The law of definite proportions, definite proportions, states that a chemical compound always contains the same elements in exactly the same proportions by weight or by mass. Okay, so table salt is made up of sodium and chloride ions. So sodium and then chlorine atoms originally. Salt, the table salt, the NaCl, is always going to be a certain percentage sodium, a certain percentage chlorine, no matter how large the sample you have of it. So definite proportions. Table salt is defined, right? Definite, that word definite, defined by being one atom sodium, 1 atom chlorine, and then the masses that are associated with each of those atoms. The law of definite proportions also states that every molecule of a substance is made up of the same number and types of atoms. So to continue with my example of table salt is always 1 sodium atom and 1 chlorine atom, Cl. That's why we say table salt is NaCl. It's sodium chloride. It's always that. It's never anything but that. If you were to add an atom, change an atom, take away an atom, you would have to change the name. It would no longer be that table salt. It would no longer be that sodium chloride. It would be something else, right? Because that's what defines table salt. Again, define definite proportions.
Table salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from. The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
So that's the law of definite proportions. Let's look at the law of conservation of mass. The law of conservation of mass states that mass cannot be created or destroyed in ordinary chemical and physical changes. Now, it can be destroyed. It can actually be turned into energy, like we see in reactions in stars. But those are not ordinary chemical and physical changes. Those are nuclear reactions. And so, yes, this rule can be broken in a way if you don't know the wording of this law. It's in ordinary chemical and physical changes. And since a nuclear reaction is definitely not an ordinary chemical or physical change, this law is A-OK as it is. But what this means for us in chemistry is that when we set up reactions and chemical equations to represent those reactions, the mass of the reactants is always equal to the mass of the products. Okay, the stuff that go into the reaction always have the same mass, total mass, as all of the products put together. And so we can see that by looking at these two sample equations. Hydrogen molecule, okay, it's H2, two hydrogen atoms make one hydrogen molecule, reacting with one oxygen atom, even though it's diatomic as well, just making it simple. Once they react together, they create one water molecule. But notice that every single reactant that was present on the left side of the reaction arrow is present on the product side of the reaction arrow. And then if we were to take these masses, okay, 3.348 times 10 to the negative 27 kilograms, and then add it to 2.657 times 10 to the negative 26 kilograms, we would have the mass of a single water molecule. Okay, 2.992 times 10 to the 26 kilograms. And so everything, every atom, and every bit of mass that is present in the reactant side of a reaction is present on the product side of that same reaction.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions, such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E=mc² equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. The law was revised to become the law of conservation of total mass and energy.
Let's finish up the fundamental laws with the law of multiple proportions. And the law of multiple proportions states that when two elements combine to form two or more compounds, right? So the difference between definite proportions and multiple proportions. Definite proportions talks about one substance being defined as having a certain structure, a certain combination of atoms. When we talk about the multiple proportions, you're comparing multiple compounds, okay, two or more. So when two elements combine to form two or more compounds, the mass of one element that combines with a given mass of the other is a ratio of small whole numbers. And what we mean here in these two examples, we have nitrogen combining with oxygen. Okay, we have nitrogen combining with oxygen. And now they're very different. Okay, one is called nitrogen monoxide, the other one's called nitrogen dioxide. We'll talk about nomenclature in another chapter. But notice that the ratio, before I get to the ratio, let's look at these masses. So we always have 14.01 grams of nitrogen. So that's 1 mole of nitrogen. So we have 1 nitrogen. We can combine with 1 nitrogen, we can combine 1 oxygen, or with 1 nitrogen we can combine 3 oxygens. Now it turns out you can actually combine a third. That'd be a nitrate. That's on something else. But notice, if we have a given amount of one substance, in this example it's nitrogen, we can combine either 16 or 32 grams of oxygen, because that is the mass of the molar mass of oxygen, molar mass of oxygen. So 1 nitrogen with 1 oxygen, 1 nitrogen with 2 oxygens. And so what's happening is there's no change in the amount of nitrogen, but we're doubling the amount of oxygen that we have. And so to finish up, we're talking about this ratio of small whole numbers. What's going to happen is we're going to take our mass, whatever the mass of oxygen is, divide it by the mass of nitrogen. Okay, we're comparing them to one another. And so we have a ratio of 1.14 to 1. Okay, 1.14 gram of oxygen to 1 gram of nitrogen. Then if we take, again, the mass of oxygen on top, okay, the numerator, divided by the mass of nitrogen, we get a ratio of 2.28 grams of oxygen per 1 gram of nitrogen. And you might be saying, hey, the definition up top says small whole numbers. The ratio needs to be a small whole number. But that's a 1.14 right there, and that's a 2.28. The ratio that we're talking about here is not of the oxygen to the nitrogen. It's the mass increase of the oxygen here. So when we make a ratio of the 1.14 and the 2.28, that's a ratio of 1 to 2. I hope you can see that just off the top of your head.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with the fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using 2 compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these 2 compounds is 8 to 16, or 1 to 2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we had the same relative amount of hydrogen.
And we'll finish up by talking about Dalton's atomic theory. So the first person to ever come up with the idea of what we would now consider an atom is a guy named Democritus. He lived in ancient Greece 2,000 years ago. And his idea stemmed from the idea that if you cut something in half enough times, eventually you'll come to an item that is actually too small to cut in half. Okay, it's an indivisible item. And that's actually what atomos means. Tomos meaning cuttable, divisible, a meaning not. It's a non-cuttable thing. So our word atom comes from the term atomos. Anywho, that was completely based in the mind. That's what the Greeks were known for, mental experiments. They actually looked down on empirical experiments, done in the physical world. They kind of looked down on it. And so that idea was never really tested in today's empirical scientific standard. But in 1808, John Dalton developed his own atomic theory. Dalton believed that a few kinds of atoms made up all matter. Now, we have 92 naturally occurring atoms. He did not think there were 92, way less. But there are a small number of atoms make up all matter. According to Dalton, elements are composed of only one kind of atom, and compounds are made up of two or more kinds of atoms. So we're getting a little bit closer to today's idea. If you want a compound, you get one or two or more types of atoms, you bring them together. And so here are Dalton's 5 postulates, and this will be what we end on today. You do want to become very friendly with this list because you will be assessed on these. Okay, so these are the 5 postulates of Dalton's atomic theory. All matter is composed of extremely small particles called atoms. Remember from that term atomos, indivisible, which cannot be subdivided, created, or destroyed. We know that's not exactly correct now because there are smaller things than atoms, things like protons, electrons, neutrons, bosons, quarks, things that we'll get into later, not all of them, some of them. Atoms of a given element are identical in their physical and chemical properties. We now know that's not exactly true because there are such things as isotopes. Again, we'll talk about that soon. Number 3, atoms of different elements differ in their physical and chemical properties. That is still believed to be completely true. Number 4, atoms of different elements combine in simple whole number ratios to form compounds. Still believed to be true. And in chemical reactions, atoms are combined, separated, or rearranged, but never created, destroyed, or changed. Again, that's still thought to be true because I'm saying here in chemical reactions. Yeah, we know in nuclear reactions, things get a little bit fuzzy, a little bit hazy, weird things happen. But in chemical reactions, normal chemical reactions, no, they're not created, destroyed, or changed. They're just rearranged. So again, data gathered since Dalton's time shows that the first 2 are not true in all cases, but they're still a very good jumping off point. All right, chemistry, that's going to do it for this video lecture. I will see you next period.